Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 23 of this course Machine Learning for Earth System Science. We are currently in module 3 where we are focusing on machine learning methods to for discovering new insights related to various aspects of earth science. In today's lecture we will be focusing on geostatistical modeling for mapping based on in situ measurements. So, the concepts that we are going to cover today are, first of all, how to reconstruct a spatial field of any variable from in situ observations. Secondly, geostatistical modeling of spatial covariance. This is a concept which we had studied in one of the very early lectures. So, today we will see some recent papers which have made use of that, albeit in a more advanced way. Thirdly, we will see how machine learning methods can be used for spatial predictions and how such spatial prediction or spatial interpolation can be validated against observations. So, first of all, let us talk about the basic idea of spatial interpolation. The aim here is to develop the complete spatial map of a particular geophysical variable y. By that I mean that I should have point wise estimate of the variable. You give me any point, any location by specifying its exact coordinates, like I should be able to give you the measurements of that of the variable which is of interest. It is not gridded observations, it is like point wise observations. But on the what basis should I construct such a spatial field? The basis is like I may have some observations obtained from some sensors like say thermometers or barometers or whatever, which are placed at only a specific points, like maybe like on top of some tower there is a wind measurement device, maybe there is a particular weather station somewhere inside a city which measures the temperature at that particular place and so on. So, these are all what is known as in situ measurements, that is I have point wise measurements at only a small number of points. And additionally I may also have observations of some covariates which are known to influence the geophysical variable y which is of my interest, and these covariates may be we may assume that these covariates are observed at all points or at least in many points. Now, the basis for making such spatial interpolation is the geostatistical equation which we had come across earlier. So, here at that time we may have denoted the variable as x, here we are denoting it by y. So, it is a spatiotemporal variable. So, we divide it into the local component, the global component plus the noise. So, now the question is how to model or mu and eta. So, the different research question basically boils down to that, how to get mu and eta. So, some highlights of that or some basic outline to that we had discussed at that time when we considered a Bayesian hierarchical model using Gaussian process and so on. But let us see what are the challenges faced in real world problems where this is used and how researchers get around them. So, let us focus on this paper which came out in 2019, a stationary geostatistical framework for soil moisture prediction in the presence of surface heterogeneity. This concept of this heterogeneity, this is the big question, the big point here. So, soil moisture is spatially variable due to complex interactions between geologic, topographic, vegetation and atmospheric variables. Correct representation of subgrid soil moisture variability is crucial in improving land surface modeling schemes and remote sensing retrievals. note the word subgrid here. I am not talking about gridded observations. Earlier I may have talked about, like when we are discussing climate networks and so on, we repeatedly mentioned gridded observations where the entire surface is divided into grids and we represent each grid by one value. So it's like we have a discrete number of measurements to be made, but in this case it's it might be continuous. That is, instead of restricting ourselves to any grid, we are going to point wise measurements in this case. In addition to the mean structure, the variance and correlation of soil moisture are affected by the underlying land surface heterogeneity. This often violates the underlying assumption of stationarity or isotropy made by classical geostatistical models. This is a very important issue. We had the stationarity is one concept which we had discussed earlier, and when we do linear the usual spatial interpolation such as kriging, one of the main concept or one of the main assumptions there is that of spatial stationarity. But in this case, what if the stationarity does not hold? The present study proposes a geostatistical framework to predict and upscale soil moisture in a non-stationary setting using a flexible spatial model whose variance or correlation structure varies with changing land surface characteristics. That is, in different parts of the region the land surface characteristics are different. The proposed framework is applied to model soil moisture distribution using in situ data in the Red River watershed of South Manitoba in Canada. It is seen that both the variance and correlation structure exhibit spatial non-stationarity for the given surface heterogeneity, primarily due to vegetation and soil texture. At the beginning of crop season, soil texture plays a critical role in the drying cycle by decreasing variance and increasing correlation as the soil becomes drier. Once the crops begin to mature, vegetation becomes the dominant driver, promoting spatial correlation and reducing soil moisture variance. So the point that we are making here is that the variance structure, if you consider the soil moisture in location S1 and that in location S2, the variance, the covariance between them is actually a function of time in different days of the year, depending on the depending on the cropping and so on. This variance relation is found to be changing. We upscale our point scale soil moisture predictions to the airborne extent and find that the upscaled soil moisture agrees well with the observed airborne data with root mean square error values ranging from 0.04 to 0.08. The proposed framework can be used to predict and upscale soil moisture in heterogeneous environments. So, the last part is related to the validation. So, we are able to make point wise predictions, but how to validate them? So, we cannot have we cannot have measurements at every point. So, what is done is they have airborne predictions maybe through remote sensing or something like that at very high spatial resolution, and the measurement, the estimates that are made using our model are going to be validated against them. So, now when we come to spatial interpolation, so earlier I was mentioned that the main challenge here is to mathematically model the local component mu and the global component eta. So, the simplest way to go about it, the way people used to do it in classically, that is the people in, let us say, in the fields of petroleum engineering and so on, where the geostatistics is very important. So, what they did is they this mu, the local component mu of ST, they represented it as in this way, x of ST times beta, where x these are basically the covariates. So, this you can say is a vector of covariates at that location and time point, and beta s, these is a vector of the corresponding coefficients. So, they basically model the local component in terms of different covariates, and now they first ignored the eta part altogether and just tried to estimate this beta based on x and y, that is they framed it as a, they temporarily forgot the eta and just focused on y, x and beta as a linear interpolation problem, linear regression problem, and solved beta. So obviously the matching will not be perfect, so there will be some residuals. So like this way you will get some value which will be which will not, even if you are trying to fit this value to y, it will not fit directly, some error will be there. So that residual, that is considered as eta. In reality it is actually eta plus the random noise, but let us forget the random noise and just say that the residual is eta. And then we then we try to fix some kind of a model, be it Gaussian process or something like that, on the eta which are obtained from the different locations at any point of time or at different points of time. So it is like you first forget eta, estimate mu, then whatever is the residual, you interpret that as eta and then fit some model on it. The problem with this approach is a loss of spatial covariance for obvious reasons. When this beta is specific to locations, that is like you are basically the mu component is like it is being measured independently at each location, while that is generally not the case. Even although mu is the local component, it is considered to be a property of a location, but even that is expected to be spatially smooth. It is not expected to vary significantly from one location to another. So you cannot really or it is a big like we are making a big approximation when we are treating the mu at every location independently. However, that is how classical geostatistics used to work. The result was the loss of spatial covariance. The covariance structure of the field, especially of a heterogeneous field, was often lost out on. An alternative is of course the Gaussian process, which we have discovered or which we have discussed in one of the earlier lectures. So this takes care of spatial covariance through parameterized covariance function. So so first let us consider that there are n locations S1, S2 up to Sn, and we are considering the y at all of them. So now instead of considering them individually, we consider they as a joint distribution, and like if you, as you remember, in case of Gaussian process, like if you consider any subset of variables, their joint distribution is always Gaussian. So in this case also, like when we are considering these n the observations of y at these n points, their joint distribution also follows this kind of a Gaussian distribution with a mean vector which we denote by this mu. So this mu is actually an n dimensional vector, and the covariance which is C, which is an n cross n matrix. So now we can like estimate the mu and C through maximum likelihood, like provided we have provided we are considering these n observations as from those locations where we do have the in situ observations. So from that we can estimate the mu and the C. Now this mu, if you like, you may want to express that mu as x times beta, the way we were saying earlier. And so basically like we can get a maximum likelihood estimate of both beta and C. Or if you want, like we can put some kind of a like a covariance structure on C or a covariance function on C and do something with it. The problem, like we can, that is what many people often do is they simply consider any stationary covariance function. Like when we are discussing about Gaussian processes, we have already talked about covariance function, and like one like simple class of covariance functions is the like the isotropic ones, where it's like considered that the basically the covariance is like I mean the variance is equal for in all cases, like for all pairs of locations. Now the stationary or it can, it need not be isotropic, of course, it can be any stationary. By that I mean the covariance of the observations at any two locations is only a function of the distance between between those two locations. That is the definition of stationarity. but if spatial variability is there, especially in the case of the data which the authors are considering in this paper, then the stationarity assumption is no longer valid. So, the alternative is to develop some non-stationary covariance functions, that is, instead of like C being a stationary, we have to somehow make it non-stationary. And the one way to do it is, we can this eta st, this the eta component which we did not consider so far, like in the statistical like neither in the classical geostatistical sense, nor in the with the Gaussian process the way it is handled so far, we have considered the eta so far. Now, we can consider this eta like as a linear combination of some certain basis functions. This is the way where we will bring the heterogeneity in. So, the this is the rough approach which has been followed in this paper. So, the approach is as follows. First, you have the in situ measurements at some of the soil moisture at some locations, at some isolated locations. So, based on that, you plot the empirical variograms for the sub regions, that is, you plot the how the covariance varies as a or the correlation between any two locations varies as a function of the distance, and you do it for different sub regions. The whole region you divide into several sub regions. In each region you plot the variogram like that, and then see are the variograms different in the different region or not. If they are not, if there is no difference, that means it's like the same region, it's a homogeneous case. In that case, you can just go to the the classical approaches. But if the variograms are found to be different, then it is necessary to basically do something like dividing the whole region into sub regions, maybe not explicitly, but implicitly, by considering the drivers of what causes this kind of spatial heterogeneity. So, like we may not know how many drivers should be there initially. So, let us denote the number of such drivers as capital M. So, for some like you have to play around a bit with the value of the capital M to know the know its optimal value. It is like somewhat like in case of clustering algorithms, the way we play around with the value of k. So, for every value of M, we have to estimate the model parameters using some process which we will see in the later slides, and once you have once you have fit at a particular model, then you have to validate it. You have to do the model evaluation. If that works, then good. If not, then you have to re-evaluate the model, and this process has to go on till we are able to do a good job of the model validation. And once you have been able to develop the model, then what you can do is you develop the you can predict the soil moisture at point support, that is, for any given point which is of interest, you can make the point wise prediction of the soil moisture or the target variable in general. And then you can for validation purposes, if it is necessary to upscale it back to the grid level, then you can do that also. Okay. So, now comes the question, how to do this kind of a non-stationary process modeling. So, this E of S, this is here I am borrowing the notation from the paper. This E is what we have been calling as eta, the global component, so to say. So, let us say that at any given location S, the E of S is like a linear combination of different drivers like this. So, just like the mu we considered as a linear combination of the different covariates, here we are considering that there are various drivers which are denoted by these E1, E2, E3, EJ, etc., and each of them have their weights. Now, the weights of the different drivers are calculated in this according to this kind of a relation by the paper. So, these x and alpha, these are like x are again those covariates which were used for mu also, and alpha is another set of parameters. So, these just like the parameters of called beta, the parameter for mu had to be estimated. So, these alpha parameters also will have to be estimated for this E. Okay. now it can be shown that the covariance between this eta at any two locations, like you can express it in this particular way. So like some kind of function has to be developed or has to be chosen. So there are again some standard covariance functions to be used. Now the problem with the estimation of these parameters beta, alpha, etc. is that we will not be able to estimate them analytically. Like in case of linear interpolation, we had the beta parameters for which we had a closed form expression. In this case, unfortunately, we will not have it. So the option is to go for non-linear optimization or numerical techniques such as simulated annealing and genetic programming. Now once you have estimated the parameters, now you are in a position to do the prediction at new points using conditional Gaussian distribution. So let us say that SP is a point where you want to make the prediction of Y, which is the soil moisture, and you already have its measurement at n other locations. So all those n measurements, they are clubbed into this variable Y. So now remember Gaussian process, whenever we have any collection of variables, their joint distribution again follows a Gaussian distribution. So so now we have total n plus 1 variables, 1 here and n here. So this subset of n plus 1 variables is again going to have a joint Gaussian distribution, which is given whose parameters can be broken down like this. Okay, so it's like this is the n plus 1 dimensional mu vector, which again can be divided into 1 plus n, and this is the n plus 1 cross n plus 1 covariance matrix, which also can be divided into blocks. Like this is 1 cross 1, this is 1 cross n, this is n cross 1, and this is n cross n. So basically once you are able to estimate these mean and covariance values, then you for the variable which you are interested in, the YSP, you can say that its conditional distribution is again a Gaussian distribution with particular mu and particular covariance. So that is how you come down from this joint distribution of YSP and Y to this conditional distribution of YSP given Y. This is left as an exercise to you. So I think when we had come across Gaussian processes, we at that time also I may have mentioned this exercise. I hope you have done it by now. So the question is, what are these the mu and C parameters of this conditional distribution? So both of them can be estimated from the mu and C parameters which we had in the original Gaussian distribution, and it should be rather easy for you to calculate the values of these blocks of C. So you can do it easily using this covariance function which we had discussed here. Okay, and for the conditional distribution, the mean and the covariance parameters, like for them we have this kind of conditional values. And now coming to the results, in this paper they have done extensive experiments. So like they had mentioned two drivers, the vegetation and the soil texture. These are the drivers of the E or the eta which they are talking about, this capital M. So in this case capital M is equal to 2, as they have two main drivers, vegetation and soil texture. And basically they have shown how these things vary over the days of the year, and so DOY here stands for day of the year, and in fact for different kinds of soil they have actually plotted this to show how different the behavior is. And like this is the study area which they have considered. So this is like you can say these are the longitudes and these are the latitudes. So this is the north south direction, this is the east west direction. So here they are basically showing how the different properties of the soil is changing from one location to another. So like basically the soil consists of these three components, clay, silt and sand. So here they are showing the percentage of the three components in different locations, and so that way you can see some clear regions. So, here is in this part there is a region which is mostly sandy. Along this part, like again a diagonalish component which is mostly clayey, and then there is one region towards the this should be the southeast, which is more mixed and which has a significant amount of silt also. Okay. And remember that apart from these drivers, we had considered the covariates also for the mu part, and the most important covariate they have considered here is the cumulative rainfall to precipitation. So, we from common knowledge we can understand that the soil moisture is directly related to the rainfall. Now, rainfall of course has a specific season, and like this is how, like across the different days of the year, this is how the rainfall is found to be varying. Now, also to show the non-stationarity of the soil moisture data, as we talked about, like it is necessary to construct the variograms in different regions. So, here they have divided the region as shown here into sub-regions 1, 2 and 3, and in each case like they have actually carried out this kind of like variogram analysis to show the variation. So, this is to basically to understand that the data is non-stationary by nature. So, these different plots are different corresponding to different days of the year, and here so here basically they have shown the results of the interpolation. So, these are the observed values of the soil moisture, it is plotted over the region, and these are the predicted values. So, when they are predicting the soil moisture, because it is coming, the predictions are being done by a conditional Gaussian as shown here. So, they need to the mean is the pointwise estimate, but they also need to focus on the variance. So, they have plotted both the mean and the variance here, and it is possible to actually correlate this the pointwise estimate, the mean map, with the actual observations and calculate some errors based on that. So, these are the error plots of the predicted values versus the observed values, and in most cases you can see a more or less like a strong positive correlation. That is, you can in all cases you can see it's like the this line, the one correlation line, almost all the points are like located around it. And so, similarly we can have the variogram analysis of the estimated values. So, like here we are on the original data we had carried out this kind of analysis. So, similar analysis on can be carried out where they are estimating the variance as a function of distance. Okay. And now we come to another paper where like basically the idea is to compare the statistical and machine learning methods for creating national daily maps of ambient PM 2.5 concentration. So, like PM 2.5 as we know is like it's a kind of particle which is used to measure the air quality. So, again the task is that like they have 829 observation stations for air quality, out of which only 200 are active each day. That is, they have sparse in situ measurements. So, what they want to do is they want to develop a pan US map of this air quality, that is a pointwise map of air quality based on only 829 observation stations, which are we can say are in situ measurements, and not only is the total number quite low, 829 compared to such a vast country as US, but only on any given day only 200 of them are active. Now, community multiscale air quality or CMAQ, this is something of a something like a process model. So, earlier also we have talked about process based simulation models. So, for air quality, this is a CMAQ is a process based simulation models which produces gridded simulations at high resolution, that is 12 kilometer by 12 kilometers. So, this is the like a traditional way of doing the building the map, but again this is based on purely based on physics. So, an alternative is to use machine learning models, say random forest, then support vector regression, neural networks, etc., where like at every location we can depend on certain predictors or covariates such as long wave radiations, relative humidity, pressure, the horizon, the east west and north south winds, etc. all of these are known to affect the air quality and PM 2.5 in some way or the other. So, like we can use all these covariates linearly or non-linearly through machine learning models to make the predictions. Now, out of all these predictors, not all of them are of course going to be useful. So, like we can choose the most useful ones through like feature selection, such as sparse regression, say things like lasso regression and so on, which like we have discussed these earlier also, where we have initially have a large pool of predictors from which we identify or pull out the most important ones. Now, the CMAQ outputs can actually be used to boost the predictions. So, like these so basically you have the meteorological covariates and as well as the land use covariates. So, now you can use something like a variable selection, as we mentioned, to like select only a specific covariates. So, in this paper they have done it and identified certain specific covariates, and then there can be some additional covariates also, and finally they have the output from CMAQ, the process model, which itself may be used as a covariate. I mean, it need not be, but it can be also used. Next the next is all these things can be fed into different approaches. So, first of all, there are different machine learning methods, such as I said, SVR, random forest, etc., which they have considered. Apart from that, they also have IDW, which is inverse distance weighting, which it is basically some kind of a special linear special interpolation technique. Then there is kriging, statistical downscaling, etc. Now, the thing is, when we are considering the like the vanilla machine learning algorithms like random forest, etc., we do not consider the spatial properties. We at any given point we try to make a point wise prediction of the like of the variable of interest, in this case the air quality, but we do not take the spatial dependence, while IDW, kriging, etc., they actually take the spatial dependence into account. So, like this is the universal kriging algorithm which they have considered. So, like here you can take a look at it. So, now like this basically shows the map of this PM 2.5. On this side you can see what is obtained from the CMAQ, and like these are the observations. So, like you can see these point-wise observations, these the points which you can see, these are the stations. As you can see that there are not only are they sparse, but they are unevenly distributed. In the like in this east coast as well as the west coast, there is a dense region, but in the vast parts of Central America there are very few of such observation stations. Now, this but if you somehow using the CMAQ process model, like if you are able to do it, you can see this kind of this kind of a map. And now so here is we are comparing the maps obtained from different approaches. This is IDW, inverse distance weighting, this is universal kriging, this is downscaler, another algorithm, and this is random forest, which is a machine learning. And as you can see, in all the different cases we get significantly different maps. Like for example, in case of random forest, we see like except for a few locations, it's like almost everything is seems roughly the same. In some of the, like in this case downscaler, like here most of the region seems to be having very low, while in this case, in case of IDW, we see significant amount of spatial variations. In this universal kriging also we see that. And it actually turns out that when they plot the results, it turns out that like the best results are obtained from the IDW, universal kriging, etc., and not from the machine learning algorithms. In fact, that's because the machine learning the models, the random forest, etc., do not in their original form, they do not take into account the spatial dependence, which is actually taken into account by kriging and so on. Further, it is shown that if these CMAQ outputs, if these are used